Imagine gazing up at the night sky, a sea of twinkling stars stretching out to infinity. Each one of those stars is a sun, much like our own, and many of them could have planets orbiting around them. The sheer number of stars and potential planets is mind-boggling. Each point of light represents a distant sun, perhaps orbited by its own family of planets. Some of these planets might be in the habitable zone, where conditions could be just right for life to exist. Could some of these worlds harbor life? The possibilities are endless. From simple microbial life forms to complex, intelligent beings, the potential diversity of life in the universe is staggering. The universe is vast, its true scale almost beyond human comprehension. With billions of galaxies, each containing billions of stars, the odds seem to favor the existence of life elsewhere. In this immensity, the possibility of other life forms, perhaps radically different from our own, becomes not just a tantalizing notion, but a statistical likelihood. The diversity of potential life forms could be beyond our wildest imaginations. For centuries, humans have pondered the existence of extraterrestrial life. Ancient civilizations looked to the stars and wondered if we were alone, creating myths and legends about beings from other worlds. Stories of strange creatures and advanced civilizations from other planets have captured our imaginations. Science fiction has explored these ideas in countless ways, from friendly visitors to hostile invaders. Yet until recently, the search for alien life remained within the realm of science fiction. Our technology was simply not advanced enough to explore these possibilities in a scientific manner. Now, with powerful telescopes and sophisticated probes exploring our solar system and beyond, the dream of finding life beyond Earth is closer than ever. We are on the brink of potentially groundbreaking discoveries. The discovery of even a single-celled organism on another planet would be a monumental event, transforming our understanding of life itself. It would open up new fields of study and raise countless questions. It would confirm that we are not alone in the universe, that the spark of life can ignite in the most unexpected places. Such a discovery would be a profound moment in human history. But what if we find something more complex, something truly alien? The implications of discovering intelligent life would be even more staggering. What if we encounter an intelligence that rivals or even surpasses our own? The implications are staggering. It would force us to rethink our place in the universe and our understanding of intelligence and consciousness. It would challenge our deepest beliefs about our place in the cosmos, forcing us to confront the possibility of civilizations far older and more advanced than ours. The knowledge and technology they possess could be beyond our comprehension. It could revolutionize our technology, our understanding of physics, and even our philosophy. The potential for learning and growth is immense. The search for extraterrestrial life is a journey into the unknown, a quest for answers to some of humanity's most profound questions. It is a journey that requires curiosity, perseverance, and an open mind. It is a journey that could change everything, reshaping our understanding of life, the universe, and our place within it. Defining life seems simple at first glance. Living things breathe, eat, grow, and reproduce. They respond to their environment and evolve over time. Yet, pinning down a precise definition that encompasses the incredible diversity of life on Earth, let alone the potential forms life might take elsewhere in the universe, is surprisingly challenging. Scientists often point to several key characteristics shared by all known living organisms. These include organization, being made up of one or more cells; metabolism, the ability to convert energy for growth and function; growth increasing in size or complexity; adaptation, evolving over generations to better suit their environment; response to stimuli, reacting to changes in their surroundings; reproduction, creating new organisms; and homeostasis, maintaining a stable internal environment. However, even these criteria have their limitations. Viruses, for example, cannot reproduce independently and rely on host cells to replicate. Are they alive? The debate continues. Furthermore, these definitions are based solely on life as we know it, life that relies on carbon-based molecules in water as a solvent. What if life elsewhere in the universe has evolved along entirely different lines? Could silicon, with its ability to form complex molecules like carbon, provide the backbone for alien biochemistry? Could life arise in the frigid methane lakes of Titan or the subsurface oceans of Europa, utilizing different energy sources and chemical building blocks? Our search for extraterrestrial life is often guided by what we know about life on Earth. We look for planets with similar conditions, liquid water, a temperate climate, and an atmosphere rich in oxygen. Yet even here on Earth, life persists in the most extreme and unexpected environments, challenging our assumptions about the limits of biology. These hardy organisms, known as extremophiles, thrive in conditions that would be lethal to most other life forms. Thermophiles flourish in the scorching waters of volcanic vents, their cellular machinery adapted to withstand temperatures that would cook most organisms. Psychrophiles, on the other hand, inhabit the frigid depths of glaciers and polar ice caps, their metabolism fine-tuned to function at sub-zero temperatures. Halophiles thrive in environments with salt concentrations that would desiccate most living cells, while acidophiles make their home in the highly acidic waters of sulfur springs and mine drainages. Even the crushing pressures of the deepest ocean trenches are no match for the incredible resilience of piezophiles. The discovery of extremophiles has dramatically expanded our understanding of the potential for life to exist in seemingly hostile environments, both on Earth and beyond. If life can flourish in the boiling hot springs of Yellowstone or the frozen wastes of Antarctica, why not in the subsurface oceans of Europa or the methane-rich atmosphere of Titan? The search for extraterrestrial life has taken us far beyond our own planet, to the moons of distant gas giants, where the conditions might be vastly different from what we experience on Earth, and the planets orbiting other stars. While we have yet to find definitive proof of alien life, several promising candidates have emerged in our solar system and beyond. These discoveries fuel our curiosity and drive our scientific endeavors. Mars, our red neighbor, has long captured the imaginations of scientists and science fiction writers alike. Its barren, rocky surface hides secrets that we are only beginning to uncover. Evidence suggests that Mars may have once been a warmer, wetter world with conditions suitable for life. Ancient riverbeds and lakebeds hint at a time when liquid water flowed freely on its surface. Today, while its surface is a dry, irradiated desert, the possibility of microbial life persisting beneath the Martian soil or in the ice caps remains tantalizing. Ongoing missions continue to search for signs of past or present life. Europa, a moon of Jupiter, is another compelling target in the search for extraterrestrial life. Its icy surface conceals a hidden ocean that could be teeming with life. Beneath its icy crust lies a vast, salty ocean, potentially containing more water than all the oceans on Earth combined. This ocean is kept liquid by the heat generated from tidal forces. Heated by tidal forces from Jupiter and its other moons, Europa's ocean could provide a stable environment for life to arise and evolve. The potential for hydrothermal vents on its ocean floor adds to the intrigue. Titan, Saturn's largest moon, is a world shrouded in a thick, nitrogen-rich atmosphere. Its surface is unlike any other in our solar system. Methane rivers and lakes dot its surface, hinting at a possible methane-based biochemistry. These features suggest that Titan could host life forms that are very different from those on Earth. While extremely cold by Earth standards, Titan's unique chemistry and potential for liquid methane as a solvent make it an intriguing candidate for life as we don't know it. The possibilities are endless and fascinating. Beyond our solar system, the Kepler Space Telescope and its successors have discovered thousands of exoplanets, planets orbiting other stars. These discoveries have expanded our understanding of the universe. Some of these distant worlds reside within the habitable zone of their star, the region where temperatures are just right for liquid water to exist on the surface, making them prime candidates for the search for life, raising the possibility of Earth-like planets harboring life as we know it. The quest to find life beyond Earth continues to inspire and challenge us, pushing the boundaries of our knowledge and imagination. When we imagine alien life, we often picture creatures similar to those found on Earth. Creatures with carbon-based bodies, breathing oxygen, and drinking water. This is largely because carbon is the backbone of all known life on our planet, forming the complex molecules that make up cells and tissues. But what if life on other planets has evolved along radically different lines? What if the building blocks of life are not carbon-based at all, but something entirely different? What if alien biology is based on elements other than carbon, utilizing unfamiliar solvents and energy sources? Could life exist in forms that are completely alien to us, thriving in environments we would consider inhospitable? Silicon, a close relative of carbon on the periodic table, is often touted as a potential alternative for the building blocks of life. Silicon atoms can also form 4 bonds, just like carbon, allowing for the creation of complex molecules. Like carbon, silicon can form long chains and complex molecules, the foundation for the intricate biochemistry found in living organisms. This has led scientists to speculate about the possibility of silicon-based life forms. However, silicon-based life would face challenges. The chemical properties of silicon differ significantly from carbon, which could impact the stability and functionality of silicon-based biochemistry. Silicon bonds are weaker than carbon bonds, potentially making complex silicon-based molecules less stable in water. This instability could limit the environments where silicon-based life could thrive. Furthermore, silicon dioxide, the silicon equivalent of carbon dioxide, is a solid at temperatures where water is liquid, potentially hindering silicon-based life from evolving in water-rich environments like Earth. This solid state could pose significant challenges for the development of life. Other possibilities exist. Life could be based on entirely different chemical frameworks, utilizing solvents and energy sources that are rare or non-existent on Earth. Ammonia, a liquid at much lower temperatures than water, could serve as a solvent for life in extremely cold environments such as the surface of Titan. This opens up the possibility of life forms that are adapted to frigid conditions. Life forms in ammonia-based ecosystems might utilize different energy sources, such as chemical reactions between ammonia and acetylene, rather than photosynthesis. These life forms would be fundamentally different from anything we know. Imagining the possibilities of silicon-based life or ammonia-based ecosystems forces us to confront the limitations of our own Earth-centric perspective. It challenges us to think beyond the familiar and consider the vast array of possibilities that the universe might hold. The universe is vast and diverse, and life may have found ways to flourish in ways we can scarcely imagine. By expanding our understanding of what life could be, we open ourselves to the endless possibilities that await us in the cosmos.